Alright, so we're looking at concavity today. Basically looking at identifying how we can pick up the shape or how a turning point or a stationary point looks. So trying to use concavity to determine what's going on at a turning point. Okay, concavity, as the name suggests, is dealing with shapes that are concave, which is like a U or a N. So to identify, there's two types of concavity. There's concave down and concave up, and as this diagram suggests, we're going to look at concave down first. Now it seems a bit counterintuitive. When you concave down, you've got a smiley face, but the way I like to think of it is the point's going down to a turning point and then getting through it. That may help for you, otherwise you can figure out your own technique for how you can remember that. This is a minimum, obviously, so it's a local minimum when we've got a concave down, so a downward facing concavity, and this occurs when our double derivative, f double dash x, is a positive value. So when our double derivative is positive, we have a downward concavity, which means we've got a local minimum occurring. Now we've looked at why that's the case. I'm not going to rehash on that. If you want to see that, you can go back and have a look. But downward concavity occurs when we've got a positive double derivative. Upwards concavity, therefore, occurs in the opposite situation, was working up to a point and then coming back down. Okay, a maximum occurs at this point in time, and obviously that means that a double derivative is negative. You all right, miss? Come in. That means our double derivative is negative there. Rather than talk through it, I'm just going to give you an example of how we can use this to figure out the concavity of our function. So I've given us question 4 from exercise 6.3, and that one it gives us the function y equals 4x squared minus x cubed, and it asks us to find the points where x provides us with a downward concavity. So straight up, get our function, derive it once, derive it twice. My second derivative function is 8 minus 6x. And this in red is where it gets a little bit trickier. Okay, so in red, I'll try and lower that down a little bit. In red, I've set my dy dx to equal 0, but rather than letting that equal 0, now I've got this side must be greater than 0. Okay, so for a downward concavity, we need a positive value, which means that our function, our double derivative function, must be greater than 0. I then rearrange that like I would any other function, take my 6x over, divide both sides by 6, and I get x must be less than 4 over 3. Okay, so any value of x less than 4 over 3 will give me a downward concavity. Okay, I'm not looking for my turning point. What I'm looking for is when things have a downward concavity. Cool. Have a crack at those. The exercises are up on the Google Classroom, so you can have a look at that.